Well, hello everyone. What do we have here? What we have is the who's who of strobe tuners, past anyway. We don't have any Petersons on this table, but we have all three Conns. And what we're going to get into in this video is first a description and a comparison of the features of the various Conn tuners. A discussion of their various pros and cons, and a discussion of accuracy. And a little bit later on in the video, we're going to have a little fun, and we're going to do some things like comparing some quartz tuners, like this little Sabine metronome, which has an A440 reference on it, and this Seiko metronome, which also has an A440 reference on it. And we'll also be comparing it to a guitar tuning, very popular guitar tuning app on the Android there, on that Galaxy S4. And we're going to see how everything fares. So before we get started, I should point out that by far the most accurate instrument on this table is going to be this Keithley 2015 THD multimeter. This guy right here has 6-digit accuracy on most measurements. Frequency, I believe it goes out at least 5 digits. Anyway, it's a very superior frequency reference to just about anything we could come up with. But I think you're going to be surprised how well some of these tuners fare versus the Keithley. So anyway, features. First of all, we have the three models here. We have the Stroboconn, and we have two Strobotuners. So the Stroboconn, the most obvious difference besides the size is the fact that it has 12 tuning wheels, and there's one for each note. And therefore, you don't have to ever change the note that you want to tune and select prior to tuning a note which note you want to check, and it's pretty much instantaneous. The two Strobotuners, on the other hand, each have a single wheel, as you can see. This is the older of the two models. This is an ST8, but virtually identical units to this can be found with numbers going much lower, all the way down to probably ST1. I don't really know off the top of my head, but I know that they made. Actually, the surprising thing is that Conn made all of these models for quite a long time. This model was originally designed in the 30s, and it was in production into the mid-70s. This is a mid-70s model, and it is virtually identical in appearance and function to the 1930s model, with just very minor iterative improvements. Same thing with this guy. This is based on a design probably from the 40s, and it was made in the 70s, and again, just functionally and physically, just almost no change whatsoever. I mean, some minor changes to the type of knob. The circuit is virtually identical, minor refinements and improvements here and there. Nothing too radical from the original. And then finally, the 70s and 80s Conn Strobotuner. I'm not sure when they originally came out with this, but I'm suspecting probably early 70s. It's an entirely solid state design. In operation, these two Strobotuners are virtually identical. This one does have a bigger wheel. The only real difference is that this one is solid state and this one is tube. This one also has a +2 function, which we'll get into. That's an octaving function there. But anyhow, so for starters, what else separates these? What else makes these different? Well, in the Stroboconn, the frequency reference is a large tuning fork, a physical tuning fork that is probably the size of 2 packs of Twix laid end to end. I mean, that's if you could visualize roughly there, you know, two inches behind this plate. And in future videos, we'll get under the hood and start really talking about these in depth. But anyway, there's a very large tuning fork, and that is the frequency reference in the Stroboconn. In the two Strobotuners, the frequency the frequency reference is electronic entirely. It is an electronic oscillator. In this device, the electronic oscillator is controlled by chokes. So the resonant frequency of the oscillator is basically controlled by various inductances on a multi-tap choke that you select with this, and then a fine tune via a choke on behind here. And when you adjust this knob, it actually distorts one end of the choke's core, moving one end of it further away from the frame to increase and decrease the inductance of that choke in very small amounts. You select your note with this, and you calibrate and fine tune and or temper with that. So that's how that one works. This one also has an electronic frequency generator for its reference, but it works more as a conventional solid-state oscillator and then a frequency divider network. Large banks of ICs that chop the input frequency down to the various ratios needed to drive it. So getting back to the commonalities, both in the case of the tuning fork and in the case of the electronic oscillators in these two units, the purpose of those circuits is to drive the motor. Each of these devices has a single motor, and the motor drives the spinning wheel. So the motor is a synchronous motor, and synchronous motors synchronous means that the motor's shaft speed is determined directly by the input frequency. So we can control the speed of the motor precisely, very precisely, by precisely controlling the input frequency of the electrical signal driving the motor. And so that is the purpose of the oscillator in all three units. Both of these, again, electronic oscillator. This one inductance based. This one, more of a traditional oscillator. This one is not quartz. That should be pointed out. It is a free running, weird oscillator prone to glitches, and we'll get into that later too. So that's it. So they all have a frequency standard, and then they also have an amplifier that drives the strobe. The strobe is positioned behind the discs in all three cases, and the purpose of the strobe is to flash at the exact rate of the frequency of the input signal, and the input signal is whatever you're trying to tune. A flute played into a microphone, a guitar plugged in, a piano mic'd, or what have you. The whole purpose of that amplifier is to take that signal and flash the strobe at the exact same frequency that you're inputting into it. And as a result, flashing frequency is represented, the flashing strobe behind the wheel flashes at the exact speed that you input the frequency. Oh God, how am I running off track here? The two frequencies are compared. There we go. The two frequencies are compared via apparent motion. So if the frequency that you're inputting in is a little bit flat of the reference frequency, then the dial will appear to turn to the left. If the frequency is sharp, then it will appear to turn to the right. Okay, there we go. Finally spat it out. Now, without further ado, let's fire up the units. So which one do we fire up first? Well, everybody wants to see the Stroboconn, right? This is probably the rarest of the units. And it is the most finicky as well. And, actually I take that back. It is the most painstaking to restore, but probably once it's in operating condition, probably the least finicky, truth be told. So let's go ahead and power it on. So first thing we do is we kick it on. Immediately the motor starts. Right now the motor is running off of wall frequency 60 Hertz, and the tuning fork circuit is warming up. This is entirely tube driven. There's two tube amps in it. There's a tube amp in the top and a tube amp in the bottom. The one on the bottom is four 6V6s in push-pull parallel that drive the tuning fork and the motor. And the one up here is a pair of 6V6s that drive the neon sign. Pilot light came on. That means that the tuning fork is now warmed up and it's ready to drive the motor. When I kick this switch over, the motor will switch over from running on wall power to running off of the tuning fork. And if I'm very quiet and the mic and this camera isn't any good, you'll be able to hear the pitch change. So I'll be quiet. And you can hear the pitch dropped. So now that we've kicked it over, now the amplifier in the back here that drives the neon light is warming up. So that should be ready in just a couple seconds. Meanwhile, let's take output here from our trusty Keithley 2015 THD multimeter, which is kindly outputting a very clean and precise 440 Hertz, which is the note A. Since it is outputting that for us, we'll go ahead and plug this in. And we can see the patterns on this dial. And now I'm going to try and adjust the intensity so that it perhaps picks up a little better. A little bit later on, I'm going to move the camera around a little closer to the devices so that you can actually see up close what's going on here. So as it's warming up, we can see very, very slight motion towards the flat on the note A, because we're supplying the note A in there. And this guy is running just a touch sharp because it's not warmed up yet. After it warms up in a couple of minutes, I'm fairly confident that that will pretty much stop. However, this is already very, 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 very close to being dead on the money, A. So while that's warming up, let's go ahead and turn on the other unit. This is the earlier Stroboconn. This is the ST8. Again, it's identical to the ST6, 5, 4, 3, just various iterations of the same thing, with the same little EV microphone. And as we can see here, this one kind of, the motor finally gets going after it's been on for a second. Now, these two here have functions that this one does not have. These two have a calibrate function. And the reason they have a calibrate function, again, is because they don't have an internal tuning fork. They have an electronic oscillator. And the electronic oscillator is much more prone to variation, and it has to be calibrated regularly, pretty much prior to each use. And the way that these two Strobotuners accomplish the built-in calibration function, when you switch either of these to the calibrate, in this case the switch is in the down position, and this tuner over here, the knob is into the first position, which is calibrate. When you switch them to the calibrate function, what they're essentially doing is comparing 60 Hertz wall frequency. That is the standard they're using, and you basically adjust the oscillator via these fine tuning knobs until the pattern stands still in the calibrate mode, and once it's been doing that for a while and the thing's warmed up, then it's pretty calibrated. It's got a fair degree of accuracy calibrating it that way. 60 Hertz is usually very reliably 60 Hertz, especially if you're in the US. Other places, I can't vouch for your power, but it's good. And there are other ways you can calibrate it too. You can simply put it in the operate mode, which is the next, or in this case it's norm, and over here it's operate. And you can supply it with a sample signal. In this case, let's take the A440 out of the Keithley and put it here in the Strobotuner and set this knob that we're tuning to A. And we can see that the pattern stands still. Now, well, it's actually fairly close. It does need to be adjusted. One of the things we see when we start using a very, very high accuracy instrument like the Keithley here in order to evaluate tuners, especially on these two guys here that have the electronic oscillators, we see a fairly, there's a good difference sometimes between when you calibrate it off of 60 Hertz wall and then when you actually compare it to a real A440. I wouldn't make that comparison just yet because these aren't warmed up. I'd probably leave these on for an hour before I would even try to get any kind of stability out of them. But nevertheless, moving right along, What are some other functional differences? Okay, so the two oscillator models, here's the other thing that kind of sets single wheel models apart from multi-wheel models. The wheel has to change speed for every note on both of these. So, you know, if I want to tune an A, I got to change this knob here, and the motor has to change speeds to represent that A. And same on there. As these get older and as the motor starts to dry out a little bit and getting in need of some oil, you will find that certain notes, when you select it, will cause the motor to kind of rattle or rumble. That's a kind of a good sign that you might need to oil the bearings inside the motor. But aside from that, once this little Strobotuner here gets warmed up, it is pretty darn stable. It's a little drifty when it's warming up, but when it reaches thermal stability, it's pretty good on the money. The Conn Strobotuner here, the 70 solid state model. Well, let's take a look at that here. Let's throw it over to calibrate mode. Okay, and we can see that the pattern is very slowly kind of inching to the right. Now let's put it in normal mode and look at the A. Well, look at that. It says the A is flat. So right there, we have a discrepancy that really means that this is going to be problematic tuning to this if you're really trying to tune with a high degree of accuracy. Ironically, that little bit of drift, that now that we're seeing a counterclockwise drift here, and again, I'll move the camera up here in a minute and we'll really look at this in depth. But the first thing, you know, I'm noticing is that when it's in calibrate mode, it shows that it's drifting a little sharp, and when I'm listening to an A440 here, it shows that it's a little flat. So that right there kind of shows the inherent disadvantage of having a single motor device where the motor has to run at a multitude of different speeds, and moreover, you have to have an oscillator which now supplies 12 different frequencies, all with a high degree of accuracy. The Stroboconn, on the other hand, circumvents that problem by simply supplying one frequency. It supplies 55 Hertz from that large tuning fork. That 55 Hertz, 55 is of course a product of 440, so 55 Hertz is just another low octave note of A. So then how does it represent all 12 notes if it only has one reference frequency? Well, very cleverly, what it does is it drives the motor at the A55 Hertz, and then inside there is a gearbox, and there are, you know, a dozen or more gears inside of that box, and each of these spinning wheels is driven off of the main shaft, which is referenced by A55. But all of these spinning wheels are gear ratioed off of the original note at precise ratios, so that they all spin at their correct note values, their correct ratios, by themselves inherently. They don't have to change speed, they're just running at the correct speed already. That's why there's 12 wheels and only one motor. The ratios of the notes are set by gear ratios. There are some very slight rounding errors that they had to deal with when designing it that way, simply because you can't have, you know, for example, a gear with, you know, 58.6 teeth. It doesn't work that way, so you have to, you know, compromise a little bit, but the compromise is so tiny and the error is so tiny that this is a very, very accurate way to do things in the real world. So, okay, so let's have a moment, now that we've explained the functionality of the various units. Let's move the camera here. I'm going to pause for a second, move the camera up closer to the Stroboconn here, and we'll take a look at really how stable it is when supplied with a clean 440 Hertz. And then we'll also supply it with some test tones from these two metronomes and a tuner app on the phone, and see what the tuner has to say about those. Okay, well, we're back. In the interim time between when I moved the camera, the Chicago Cubs won the World Series. Go Cubbies. All right. So, while we're on this zoomed up view, let's take a closer look at first the reference frequency. Now, the Stroboconn has had a good long time to warm up and stabilize. So let's recalibrate it to the Keithley. So I'm plugging in the 440 Hertz from the Keithley, and it's a little bright for the screen, so I'm going to reduce the signal until we get a clearer image on the screen. There we go. To the naked eye, you can actually view it in the previous state that it was in. It definitely has more definition turned down like this. And really all this knob is doing is adjusting the input gain of the signal. It says control, but really all it is just an input gain. You know, just think of it as a volume knob essentially. So now that it's good and warmed up, and we're talking a couple hours since the last footage was shot, we have just the tiniest drift to the sharp side, which means that the tuner is running a little flat. So if we just kind of feather that big knob, well, unfortunately I'm zoomed in a little too far to show you that knob, but right below this dial here is a big knob that allows me to adjust that dial. So, well, just for fun, I mean, even though it's kind of stabilized, and I'm loath to take it to the extremes, let me just show you what happens when we take it all the way to 50 cents sharp here. You can see that the apparent measurement is that this is flat, which makes sense. If we set this thing 50 cents sharp, a real 440 should measure flat, and we can see that by the direction that the pattern is spinning. And then likewise, if I turn it 50 cents flat on the dial, and I'm not sure if the mic is picking up, but you can actually hear the motor change pitch. I'm going to shut up for a second and move the dial from one extreme to the other so you can hear the motor change pitch when I do it. I hope the camera picked that up. Anyway, so let's get it zeroed out. Now, a very high degree of accuracy is possible with this unit. I believe the manufacturer says that 0.15% is the tolerance, and I can get it one decimal place further than that, actually. And I think that even tighter tolerance is possible if the variable tuning mechanism is disabled. If you were to disable, and I have some methods that I might do videos on, some advanced videos on restoring this unit. In fact, please message me if you're interested. If you have a Stroboconn and you're interested in restoring it, I put a lot of time and effort into figuring out how to properly go through this unit and calibrate it. And so reach out to me if that's the case. Anyway, let me get this thing good and zeroed out. And there we go. It's not anywhere near as touchy. I mean, you know, the fine tuning is a little bit touchy, but it isn't anywhere near as touchy as, for example, the other two Strobo tuners, and we'll get to that in a little bit. But right now, while we're zoomed in on that A, and we got a good image, and we can see that the Stroboconn is completely synced up to the 440 reference tone of the Keithley meter, which we're using as our frequency reference. So, getting back to the microphone, let's go do those tests real quick so we can really see how bad those other tuners were. First is a little Sabine zip beat, a very common metronome that has a 440 reference tone that you might tune your guitar to. Let's take a look at the screen here and see how it's a little blown out. It's definitely tough to adjust the neon tube to a range that doesn't blow out the camera, but as we see, you see a drift to the sharp. The A wheel is rotating counterclockwise, which indicates sharp. Well, it's not so much counterclockwise, it's moving to the right, which indicates sharp, because obviously the wheels in the top spin in opposite directions. So all the sharps and flats up here, you know, it's not, really shouldn't be thought of as counterclockwise and clockwise like I just said. It should be thought of as right and left. If it moves right, it's sharp. If it moves left, it's flat. And there we have it. A good clear image that this little zip beat tuner is in fact sharp. Okay, let's shut it up. Let's go back to the little Seiko tuner here. And by the way, I've shot so much trial and error footage here that if I'm saying going back to something that you haven't seen yet, then please forgive me. But anyway, here we have a Seiko metronome that also has a tuning function, just like the Sabine Zip Beat does. And here we can hear its annoying beep. Put the microphone up to there. And again, we can see that this is also sharp. It's not quite as sharp as the Sabine, but it is in fact a little bit sharp. And I have high confidence in these measurements because, again, we just calibrated this thing to a Keithley 2015 THD, which is a sufficiently accurate frequency generator to be making these kinds of measurements. Let's see here. Let's go back to the Guitar Tuner app on my phone, and let's have it produce, let's start with an A, and we'll tell it to sound the A, and there we go. It's doing an A880 for some reason instead of an A440. I'll have to look at the settings. But look at that. It's that bottom ring there. And that brings me to how strobe tuners work. Each ring represents an octave. So because this is A880, we see that second to last ring showing the main pattern rather than the one above it, which we were seeing on the 440 tone. But as we can see, my Samsung Galaxy S4 here with this Guitar Tuner app is generating a very flat A. And, you know, the error that we saw on these two little quartz tuners is definitely there, but it's definitely debatable whether it's audible. I mean, you certainly couldn't, you know, use it as a reference tone to temper a piano or something like that. But, you know, for tuning a guitar, you'd be fine. But honestly, the A is so far off on this Guitar Tuner app that I would just be horrified to use it. Now, interestingly, I don't have the rig set up to do this. I don't have a speaker, although we'll do that in another test. But I need some way to pipe a signal into this if we were going to test this phone and this app's ability to measure a signal being input to it. I've done it before, and I've found that it is also wildly inaccurate. And we can try different notes too. That was an A. Since the Stroboconn can show us any note, let's try G. Let's go down a whole step and try a G. Now look at that. The G natural is wildly sharp. Now that's really interesting. And here we see the pattern. It's moving very fast to the right. The G natural is incredibly sharp. So, let me get this straight. The A is wildly flat, and the G is wildly sharp. Oh, that's really pretty appalling. Let's try an F. Let's go down another whole step. Well, that's interesting. It's flat, but it's a lot closer than the other notes were. Let's try an E. Flat. Wow. The D is flat. Again, probably about as flat as the F was. Not incredibly flat, but still way further off than either of the other two tuners were. And the C is sharp. Look at that. All the way over here. Look at that. So flat, sharp, flat, sharp, flat, sharp, flat on the naturals. Let's try the flats and sharps. So we're looking at the upper windows now. So we're doing a C sharp. We're looking here, and again we see it is sharp. Let's do a D sharp. It's flat. Amazing. F sharp, way sharp. Look at that, it's hauling ass. I'm not even sure if the camera's picking it up, but it is hauling ass to the right. That is farther out than any of the notes so far. G sharp. Sharp as shit as well. Wow. A sharp. Sharp, but not as sharp. So, I only did the B natural. B natural's flat. Okay, so every note's off on the tuner app. If there are any Android hardware, software people out there, I suspect that this is a mathematical problem related to dividing hardware frequency cycles in correct proportions. But if anybody out there who's a developer who knows anything about that would care to hazard a more educated guess as to why that application is just so completely far off, I would love to hear it. Okay, so wow. We just checked 3 very common methods that people use to tune their instruments, and they're all off. That's pretty sad. And just to show you that there's nothing funny going on here, I'll plug that A440 test tone back in, and look, bam, dead on. And I'm going to pan the camera over here. Oh well, I need to bring the light down a little so you can see that it's dead on. There we go. So I just brought the input gain down a little bit. Again, this is just adjusting the input gain of the signal, which ultimately affects the intensity of the lamp. And too much intensity, the camera can't handle it. But as you can see, the Stroboconn and its 55 Hertz tuning fork is still completely deadlocked to the Keithley. And we'll just pan over here a little bit so we can see there's the Keithley down there. Wow, I've got this tripod locked hard. Okay, I'm not going to pan down to better frame the Keithley, but there it is, putting out 440 Hertz. And so, okay, very cool, right? So I guess the next thing we need to do is we need to see how the 2 smaller Conn tuners do when good and warmed up, and that's going to take some rejiggering of the camera as well. I think at some point in future videos I'm going to touch on actually how to use this unit. This thing with its 12 wheels has an amazing capacity to show you spectral components inside of notes. You can play a keyboard on a pipe organ patch, for example, and actually see where there's a strong 5th and a strong 4th, and so on, and it's very educating as to which of those harmonics are in tune and not in tune with the fundamental. That gets to instrument temperament, which is something I don't know a whole lot about, but I do know enough to tell you that mathematically speaking, if you were to tune an instrument purely to mathematical reasoning. I mean, doubling of the octaves, but also of the exact proportions within the octave. You wind up with something that doesn't make very pleasant sounding chords. And so most instruments are tuned with a temperament that slightly alters the pitch of certain parts of the scale in order to produce a more pleasant sounding chord. And you can actually see this. In fact, this thing is so sensitive you can see a lot of things. When I hook up a microphone, and I'll do this later, this little experiment, you can actually see the Doppler shift of moving a sound source towards and away from the microphone as it plays. The Doppler shift shows up as a wobbling in the wheel, and it's very obvious and pronounced. This is an incredibly sensitive instrument. It displays the difference between two frequencies more accurately than just about anything I can think of. The Keithley over here is certainly more precise at both measuring frequency and providing a reference frequency that is dead on the money. However, the Keithley is not terribly useful for tuning an instrument. When you have a Stroboconn that is properly calibrated, and again, I do mean properly calibrated. The tuning fork in this thing is quite a challenge to actually get it so that when the needle's pointed at zero, that the instrument actually zeroes out like this against a reliable source, not against a cheap tuner, not against a phone tuning app. I mean, God forbid against a phone tuning app, apparently. I shudder to think of musicians who record and perform for paying patrons having tuned their instruments to their phone after some of the experiments I've done. I mean, this is just one phone, granted, what I showed you, but I have checked other phones, and let me tell you, they vary. I would like to do some experiments with Apple phones. I haven't done much experiments with them. I'm hoping they might fare better simply because the hardware is more predictable in its performance from a developer standpoint. It's, there's far fewer variants of hardware to take into consideration when writing a program for the iPhone than when writing it for the Android. So it could very well be a function of the Galaxy S4, the software I tried, and I've tried a couple different apps, not just the one I mentioned or didn't mention. All right, coming up next is a closer look at the two more affordable, more accessible, and certainly more plentiful Strobo tuners. The Stroboconn, we'll keep it up here for now, and we're going to use it as a reference. And it's going to be some fun times here. If anybody has any suggestions about things they'd like to see in this tuner shootout here, I'm all ears. I don't have any Peterson tuners to test against either the Stroboconn or its little nephew and niece, or the Keithley that I'm using as my master reference here. So if anybody got an extra Peterson laying around they want to send me for some testing purposes, do reach out. For now, this is kind of it for this particular video, but there will be more coming up very shortly. Cheers.